This lesson is going to take a look at systems of equations. Systems of equations can be very helpful in solving a lot of real-world applications, and we like them because we're just going to look at systems of 2 equations, but a lot of times there's 3 or 4 equations involved, and you're trying to figure out where everything intersects, how all of these different components of a problem fit together. So an example of a system of equations is shown here. Again, like I said, this is a 2 by 2 system, meaning that we have 2 equations and 2 variables. And we need the same number of equations as variables. We can have more equations, but that doesn't necessarily help us. But we need a bare minimum of 2 equations if we have 2 variables, 3 equations if we have 3 variables. We need at least that much information, or else you're just solving things in terms of each other. And we'll talk about that a little bit as well. So in this case, the a's here are just coefficients on x, the b's are just coefficients on y, and the c's are just constants. So some possible options, like I said, we're trying to figure out where things intersect. There's 3 different possibilities that we can have when we are looking. Again, a solution is going to be a set of numbers, because we're always going to have at least 2 that make both equations true simultaneously. So, a couple of options here. First option, which is what we like to get, is if these 2 things, these 2 graphs, these 2 lines intersect at a given point. So if you were looking here, this just so happens to be at 2, 2, which is just coincidental to it being a 2 by 2. But we have some kind of intersection. And we have only one solution. So this is nice. It gives us that, ordered pair, that set of numbers. Another option we can have is if these 2 lines run parallel to each other. So if they are parallel, as you can see from the graph, they don't intersect. So we have no solution. And while this might be disappointing, it's also at least a concrete answer. The third case is if we actually have a line and then some other variation, but it's exactly the same line. And so in this case, we have identical lines. And in this case, we have infinite solutions. So let's take a look. The one way we can do this obviously is by graphing these lines. It's not the best way to do it, but I'll go through it quickly. This is a lot better to do if you do have a graphing utility. If you do have a graphing utility, then this is a perfectly acceptable method. If you don't, then it's a little iffy as to whether you will graph it properly to make sure that you have the proper intersection. You want to make sure you have graph paper. You want to make sure everything is lined up properly if you're going to try this method. So if you're going to do this method, we'll, for instance, take this top equation, negative 2x plus 4y equal to negative 6. If we're trying to find that point of intersection, solve the system, we're going to rearrange this to put it in slope-intercept form so we can graph it. If we do that, we would move the negative 2x to the other side, so we'd have 4y equals 2x minus 6. We would divide everything by 4. And then we'd end up with y is equal to 1/2 x minus 3/2. So if we want to graph that, and I'll graph it in blue, I'm assuming that each one of these marks that I have is 1. Again, you always want to make sure you label your units when you're graphing. We're going to start at negative 3/2 here, and then we're going to go up 1 over 2, up 1 over 2. And so we get this line here. If we take our second equation here, 3x minus 2y equals 9. Again, we are going to move that 3x to the other side, so we have 2y is equal to negative 3x plus 9. Divide through by that coefficient negative 2. And we get y is equal to 3 halves x minus 9 halves. This one we're actually going to start at negative 9 halves. So that would be about 4.5, or would be 4.5, negative 4.5. And then again, we've got a positive slope here, so we're going to go up 3, 1, 2, 3, and then over 2, and then up 3 again, so 1, 2, 3, and then over 2 here. And we will see that these indeed cross. They're actually supposed to cross here, and like I said, I didn't do the best job drawing them here, but they are supposed to cross here at the intersection point. Which is 3, 0. So right there on the x-axis, these are supposed to intersect. Like I said, if you had a graphing utility, it's a little bit better. Let me show you how to do that. Go ahead and get your graphing calculator out if you have one. So if you have your calculator, if you go over here to y equals, again, in the slope-intercept form, type these in. So we have, in this case, it would be x over 2 minus 3 halves. And hit enter. And then the other one, we have 3x over 2, or 3 halves x, depending on how you want to write it. Just make sure that you put the parentheses around the 3x if you're going to do it. And then minus 9 halves. And then we go to graph. You can see that first line that we had there, and then the second line that we had here. And you can see here that they do look like they intersect here. We can check this by going second and then calc. We've got intersect here, number 5. We grab our first curve, hit enter, second curve, enter. We only have 2 curves. And then we want to try to get a little bit closer to the point that they actually intersect so our calculator can do it quickly. And then we hit enter and we see that our intersection is here at 3, 0. So we can confirm what we had in our graph. So like I said, this is one way to do this. It's not the most effective method. The next 2 videos are going to talk about some other methods that are going to be a lot more helpful.